Now let us see what are the applications of the Zener diode. Generally, the Zener diodes are used in three main applications in the electronic circuits. They are: the Zener diode is used as an voltage regulator. The Zener diodes can be used as a waveform clipper, and the Zener diodes can also be used as a voltage shifter. Now let us discuss one by one in detail. First, coming to the voltage regulator. This is most common application of the Zener diode. Now let us see how we can define the voltage regulator. A voltage regulator is a device used to provide a constant output voltage to a load connected in parallel to it irrespective of variations in the energy drawn by the load, that is the load current, or the variations and the instability in the supply voltage. Now if you see here, this is the appearance of the voltage regulator. And the combination of elements present in the design of the voltage regulator ensure to have a constant output voltage with a variable input supply. And this application of the Zener diodes relies heavily on the ability of the Zener diodes to maintain a constant voltage irrespective of the variations in the supply or the load current. Now let us see the application of the Zener diode as a voltage regulator. Now if you see here, this is a circuit diagram showing the Zener diode being used as a voltage regulator. Now let us see the working principle of the voltage regulator. A resistor Rs is placed in the beginning of the circuit. This is the resistor Rs, which is placed at the beginning of the circuit in order to limit the reverse current through the diode to a safer value of the resistor. So it limits the reverse current across the diode, and the source voltage Vs and the resistor Rs are so selected that the diode operates in the breakdown region. This is the supply voltage Vs and this is the resistor Rs, and these two are selected for the diode in order to operate in the breakdown region. And the voltage across the diode is known as the Zener voltage Vz, and the diode current is known as the Zener current Iz. So now if you see here, this is the Zener diode in which the voltage across the diode is represented as Vz, whereas the current flowing across the diode is represented as Iz. And a steady state voltage is maintained across the load RL as the output voltage fluctuations get absorbed by the resistor Rs. So across the resistor RL, we need to maintain the steady state voltage so that the output voltage will not be fluctuated by the resistor Rs. And the input voltage whose changes are to be regulated connects the Zener diode in reverse bias condition. And the diode does not conduct unless the voltage across the RL is less than the Zener diode breakdown voltage Vz, and the Rs and the RL constitute a potential divider across the Vs. So that's why until the voltage across the RL is less than that of the breakdown voltage Vz, the diode does not conduct, and the resistors Rs and the RL are connected as a potential divider across the Vs. And as the supply voltage Vs is increased, in this case the voltage drop across RL will be more as compared to that of the Zener diode breakdown voltage. Now as the value of the Vs is increased, then the voltage drop across the RL also increases compared to that of the Zener breakdown voltage, and thus it causes the Zener diode to conduct in its breakdown region. Hence, the Zener current Iz is limited by the series resistor Rs from exceeding the rated maximum value Iz max. The current through the Rs is given by Is is equal to Vs minus Vz by Rs, whereas the source current gets split into Iz and IL at the junction, which is given as Is is equal to Iz plus IL. And the voltage across the Zener diode Vz remains constant until it is operated in the Zener breakdown region through the Zener current Iz, which may vary considerably. Now if you see here, this is the VI characteristics for the Zener diode, in which this is the Zener voltage and this is the applied input voltage. And if here the input voltage is increased further, the current through the diode and the load increases. As the resistance across the diode decreases, this will cause more current to flow through the diode. As a result, the voltage drop across the Rs will be more, thus the voltage at the output will be the value that is close to that of the input or the supply voltage. Hence, we can say that the Zener diode maintains a uniform voltage across the load unless the supply voltage is more than the Zener voltage. And here we can observe the output voltage Vout to be equal to Vin minus IR. The next application is the Zener diode as a waveform clipper. So this is another application of the Zener diode, which is the waveform clipper. Now let us see how we can define the clipper or the clamper circuits. The clipping and the clamping circuits are the circuits that are used to shape or modify an input AC waveform or the signal, which produces a differently shaped output signal depending on the specifications of the clipper or the clamper. And the clipper circuits generically are the circuits that are used to prevent the output signal of a circuit from going beyond a predetermined voltage value without changing any other part of the input signal or the waveform. And these circuits along with the clampers are widely used in analog television and FM radio transmitters for the removal of the interference and also for limiting the noise peaks at the high peaks of the signal. Now let us see what are the types of the clipping circuits. The clipping circuits could be designed to clip the signal either in the positive or the negative or in the both of the regions. So depending upon this, the first type of the clipping circuit is the positive clipper circuit. In this kind of clipper circuit, some part of the positive half of the input signal is eliminated or removed, whereas there will be no variation in the negative half of the input signal. If you see here, this is a circuit for the positive clipper, in which this is the voltage source. This is the Zener diode with the voltage 6.2 volts. And this is the resistor with 1 kilo ohm resistance. And when the input voltage is larger than the voltage source connected with the diode, then the diode will cut the larger voltage and the output voltage will be equal to the biased voltage. That's why if you see here under the positive half cycle of the input signal, we can observe the signal which is clipped. Whereas under the negative half cycle, it is completely shown. So during the negative cycle, there is no variation in the voltage and this cycle will be shown completely at the output. For example, if the voltage at the input is 5 volts and the biasing voltage is 2 volts, then the output voltage will be 2 volts and the other 3 voltage will be cut by the circuitry. And this is due to if the input voltage value is lesser than that of the voltage source connected with the diode, then it behaves in the reverse bias condition and it will stop the biasing voltage flowing through the diode. Whereas if the value of the voltage is higher than the bias voltage, then the diode works in the forward bias mode and current starts to pass through the load resistance. Now coming to the second one, that is the negative clipper circuit. In this type of clipping circuit, some portion of the negative half cycle of the input signal will be eliminated or removed and there will be no effect on the positive half cycle of the input signal. Now if you see here, this is the circuit diagram for the negative clipper circuit, in which this is the Zener diode and this is the resistor and this is the voltage source and this is the biasing voltage. So if the applied voltage at the input has a positive value, then the diode will be in the reverse biased mode. Now in this case, if the negative half cycle of the input voltage is higher than that of the biased voltage of the diode, then the diode works in the forward bias condition and the exceeded value will be removed from the waveform. So if you see here, under the negative half cycle of the input signal, we can observe the clipping of the signal, whereas under the positive half cycle of the input signal, the signal is completely shown. And the third type is the double Zener clipper circuit. So this is the circuit which is used to implement the clipping circuit for both the negative swing of the AC circuit as well as the positive swing of the AC circuit. And that's why it is called as a double Zener clipper circuit. And in the double Zener clipper circuit, the voltage is clipped at different levels on the positive and the negative swings of the output waveform. Now if you see here, this is the circuit diagram for the double Zener clipper circuit, in which this is the source resistance RS and these are the two Zener diodes Z1 and Z2. That's why it is called as a double Zener clipper circuit. If you see here, we can observe under both the positive half cycle of the input signal and under the negative half cycle of the input signal, the signal is getting clipped. And the last application is the Zener diode as a voltage shifter. The voltage shifter is one of the simplest but interesting application of the Zener diode. Now let us see how we can define the voltage shifter. Voltage shifter helps to convert the signal from one voltage to another voltage, and with this ability of the Zener diode, it maintains a steady output voltage in the breakdown region. And in a Zener diode biased voltage shifter, the circuit lowers the output voltage by a value equal to the breakdown voltage of the Zener diode that is used. Now let us see the circuit diagram for the voltage shifter. If you see here, this is the circuit diagram for the voltage shifter, in which this is the Zener diode and this is the input voltage and this is the output voltage and this is the resistor. Now depending upon the voltage across the diode and depending upon the input voltage, the output voltage gets shifted from one voltage to the another voltage. So this is how the operation of the Zener diode takes place as an voltage shifter. So